Friends, we are here again with fluorescence spectroscopy. So, today we will talk about this various photophysical processes. So, once we generate the excited state, what is going to happen to this excited state molecule or excited state species? So, excited state what next? Okay, so what is going to happen with the excited state? So, three things, broadly three things may happen. One is photophysical process. So, photophysical process, this is one. Number two can be photo-induced electron transfer or charge transfer, better to say charge transfer. Generally it is given PIT, photo-induced electron transfer, or general term is photo-induced charge transfer, and third option is photochemical reaction. That is the reaction initiated by photon, that means real chemical process can happen. So, so let us start with photophysical process. What is photophysical? Okay. So, photophysical processes can be like, as I discussed in my last lecture, that radiative process, one can be radiative, another can be non-radiative. So, it can be once excited state is created. Okay. So, two things can happen separately, like maybe radiative de-excitation that gives rise to two things, fluorescence and phosphorescence. These two things can happen. So, both of these two give rise to H nu F or H nu P. Of course, this is in bluer side and this is in the redder side. So, bluer side of the spectrum and this is the redder side, red side, that is lower energy side, red side or lower energy side of the spectrum. Okay. So, these are the two things, and of course, fluorescence is a spin conserved radiative process and phosphorescence is spin forbidden radiative process. So, these two are mainly the radiative de-excitation, and apart from radiative de-excitation there can be non-radiative processes. Although I have shown you in my last lecture some pictures where I have shown certain upward arrow, then certain downward arrow, some dotted arrow or maybe some squiggly arrow, downward arrow. So, these arrows have significance. Okay. So, basically non-radiative processes, I mean it is also a photophysical process. So, non-radiative processes, okay, one will be state to state crossing, that is crossing from one state to another that is maybe singlet to singlet or maybe singlet to triplet. So, singlet to singlet, one state say Sn to Sn minus 1 or maybe Sn to say Tn, okay, or maybe say Tn to Tn minus 1, okay, or maybe Tn to Sn. So, there may be several possibilities depending on the specific nature of the molecule and the available states. State to state crossing means various types of state to state crossing may be there. Another is called vibrational relaxation. Vibrational relaxation, what is that? So, think about this Morse potential like this. So, these are the vibrational lines, I mean this is a vibrational ladder, vibrational states. So, suppose we create, because of say photo excitation, suppose this is the excited state potential energy diagram and say this is the ground state potential energy diagram. So, transition takes place say from here to say up to this, say for example. Say here, okay. Say or transition originates from this state and ends at this state. Suppose this is I am considering a particular transition. So, then what will happen? Now, this is a vibrationally excited state of the first electronic excited state. So, this is your S0, say this is S1. So, this is vibrationally excited vibrationally excited S1. So, what will happen? So, possibility is that the molecule, I mean this system may relax, I mean come back radiatively from here to here maybe, or maybe here to here or here or here, or maybe other possibility is that this there will be vibrational relaxation so that this it will relax from the vibrationally excited to the lowest vibrational level like this. It is given this squiggly arrow, and then maybe what will happen after this, it may undergo another transition from here to here, maybe radiatively or maybe non-radiatively. Okay. So, if it happens radiatively, then it will be fluorescence, or if it happens non-radiatively, then it will be a non-fluorescent, but it maybe this excess energy will be given to the system in the form of heat. Okay. So, this is what is called the vibrational relaxation. Okay, that is a vibrationally excited state will relax to the corresponding vibrational ground state of that particular electronic state, and then other things may happen. Okay. So, what other can happen that there will be a combination of radiative and non-radiative de-excitation processes. That means system may not be like this, that only radiative de-excitation will happen and non-radiative channels are blocked. It may not happen, that both the channels may remain open, so that both processes combined radiative and non-radiative processes combined radiative and non-radiative processes can take place, I mean can occur. Okay. So, this may be the third possibility. Okay. What else can happen? There may be there may be energy transfer. Energy transfer means that this see, we are talking about the fate of the excited state. So, suppose we have got one molecule, say system A to A star. Okay. So, this A star, that means it is having additional excitation energy. So, what will happen? It will transfer this energy to another molecule. To another molecule means the molecule which is in close proximity to it, or maybe this may be one possibility, and the other option could be excited state complexation or excited state complex formation. So, this is energy transfer, or maybe other possibility is excited state complexation or excited state complex formation. And under this heading broadly there are two things, one is exciplex, another is excimer, that is excited state complex and is an excited state dimer, that means of which one is in excited state, other is in ground state. Anyway, I will come to this. So, radiative process, as I told you, photon is emitted and molecule from the excited state to the ground state, that is molecules will go automatically will go from the excited state to the ground state. So, this is a radiative process, and as I told you that excitation energy is dissipated in the form of heat. What is that is your vibrational relaxation. So, due to this vibrational relaxation, this excess energy, this much of excess energy is dissipated to the surrounding in the form of heat, this excess energy, this excess vibrational energy. Okay. And crossing from one electronic level to another with a lower energy, the excess energy is converted to vibrational energy, electronic vibrational coupling, this excess energy being converted to vibrational energy. So, that also may happen, or vibrational energy thereafter may be converted to to heat. Okay. So, in both the cases this excess vibrational energy will be converted to heat. Okay. And another thing is that in the excited state, these are all physical processes, that no change in the chemical composition or the chemical nature of the system is there, the molecule is there, but the other option is excited state can be used up in producing chemical reaction, in giving rise to chemical reaction. Okay. So, that means it is an excited state reaction, that is maybe some bonds are broken, or maybe some rearrangement takes place. So, that may happen. So, that is through the excited state of the molecule. Energy transfer and excited state complexation. Now, this occurs when more than one molecule are undergoing interaction. That is, more than one molecule means suppose we have got one A, say another A star, or maybe one A, another B star, or maybe one A star, another B. So, these two are undergoing interaction, maybe these two are undergoing interaction, or these two. Okay. So, minimum aggregate will be a dimer, or a heterodimer like this. Or a heterodimer. Okay. So, these are the two possibilities. So, in this case you should keep it in mind that when there are when there are interaction between more than one species, of which one is maybe in the excited state, then dimer formation or maybe complexation is a possibility. Okay. Now, exciplexes are formed when one of these two different molecules, say basically say this or that situation, means one of these two is in the excited state, that is excited state complexation. Basically what is happening, that there is no, suppose there is no ground state interaction, means suppose we have got a molecule say pyrene, okay. So, if you excite this molecule say at 337 nanometer, close to its absorption maximum, then it will say this is written as PY. So, it will become pyrene star in the excited state. Okay. And then if you add from outside, and suppose say this is a micromolar concentration say of the order of say micromolar. Okay, concentration of pyrene is micromolar. Then pyrene star, and suppose if you add from outside to this excited pyrene, that is pyrene star, if you add say DMA, dimethyl aniline, in the ground state, NMe, dimethyl aniline, say in some say maybe in benzene, okay, in dry benzene or some less polar solvent, then there will be some charge transfer, okay, and as a result of which, if this is written as DMA, then pyrene star, this will be basically dot minus and DMA plus dot, this two will form excited state complex. This is a pyrene DMA, this is called pyrene DMA exciplex, and this exciplex is formed when pyrene is in the excited state, not in the ground state. So, there is no ground state interaction between these two. Okay, so, what you expect that because of this formation of this exciplex, it's a new transient species. Okay, its characteristics are different compared to that of pyrene star or maybe pyrene. Therefore, you can expect a different spectroscopic signature for this heterodimer formation. This is called a heterodimer. Two molecules are there, and two molecules are there, but these two molecules are not similar. I mean, not pyrene or maybe not 2 DMA molecules are there. But and there can be other possibility that if the concentration of pyrene is sufficiently high, I mean it's high, like say 10 to the power minus 4 or 10 to the power minus 5 molar, then pyrene forms excimer, excited state dimer. So, that is of course in the means in that case it may form pyrene excimer. It is a excimer or excited state dimer, but this is a heteroexcimer. Okay. Now, next is photo-induced electron transfer or PET. So, this is another FET is photo-induced electron transfer. This is PET. Okay. So, photo-induced electron transfer, I mean under this heading there can be photoionization, or there can be other things like electron transfer. Okay. So, let us come one after another. So, what is that now? One is photoionization. So, what will happen that an excited species may easily lose the electron. Okay. So, giving rise to some ionized species. So, say maybe M star, then maybe plus electron or maybe minus electron, giving rise to say M plus dot or maybe M minus dot. Okay. So, this is basically ionized species. Okay. And another possibility, I mean under the heading of photo-induced electron transfer, there can be electron transfer. As I told you, like this pyrene DMA case, pyrene plus DMA case. So, this is purely a photo-induced electron transfer from DMA, ground state DMA to excited pyrene. Okay, so it is a clearly an electron transfer case. So in both the cases, whether there is photoionization or maybe you know I mean electron transfer, in both the cases charge has been transferred. Okay, in case of photoionization, this additional electron, I mean whatever electron is added or released, that may be given to, you know, solvent or maybe some other entity who is accepting the electron. Okay, now photochemical reaction. So there may be, so under the heading of photochemical reaction, I mean this is also a fate of, you know, excited state. So there may be, you know, photochemical reaction. What are those possibilities? One is maybe photoisomerization. Okay, that means some isomer, I mean bond rearrangement or something. I am not going into the details of it, because photochemical reaction and this photochemistry is a separate you know, issue that may be taken up in some other, you know, some other courses. There may be photo decomposition. There may be photo association, and it is basically a reaction. It is not like excited state association like, you know, Excimer or Xeplex. It is not that. It is a true chemical reaction, and association, I mean association means dimer or, you know, or polymer formation. So photo association. And last is photobiology, like, you know, this reactions that is, you know, like reactions that are relevant in photosynthesis. These are also very important. So these are all related to photochemical reaction. Means after you know, excited species is formed, then this particular excited state may undergo several things. One may be, like, one of which is photochemical reaction, that is real chemical transformation. So, you know, together means whatever I, you know, talked about, if you think of, I mean if you just consider the photophysical processes, then you know this is a composite diagram which is called the Jablonski diagram, where this is your starting state is 0 and you are exciting the molecule, I mean the system. Maybe say this excitation occurs to S2. Okay. Then there is vibrational relaxation giving rise to you know vibrationally relaxed S2. Then from S2 there is internal conversion, that is there is no change in spin state, which is called the internal conversion, to maybe somewhere over here, and then there is a radiative de-excitation to here, maybe here or maybe here or maybe here also there is a possibility. So this is your fluorescence. Then there is non-radiative intersystem crossing, that is state to state crossing. This is also one state to another state crossing. So this is intersystem crossing. So S2 to say T2, then vibrational relaxation giving rise to the lowest lowest vibrationally de-excited T2 state, that means triplet state number 2. Then there is internal conversion, because T2 to T1 is an internal conversion. Okay. So this squiggly arrow or this and these state arrows. So squiggly arrows are basically non-radiative processes, and direct arrows are basically radiate. Downward direct arrows are radiative processes. Okay. So from here to here there is a radiative de-excitation. Of course, there is no conservation of spin from T1 to S0. Okay. So that means T1 to S0, that means it is since it does not conserve spin, so therefore it is a spin forbidden. But this happens, this occurs, but of course kinetics wise this is slow. So this is called phosphorescence. So this is a composite representation where this additional heat maybe here, or maybe from here to here. So, this excess heat, I mean vibrationally excited energy, excess energy has been given to the surroundings, okay, in the form of heat. Okay, so, this is a composite representation. Now, next let us come back to photophysical process. Some chemical processes are initiated by photoexcitation, and hence their kinetics should depend on rate of formation of the excited state. That is very important, that this is this photophysical or some chemical process, since that is originated from your excited state or which depends on photoexcitation. Therefore, kinetics of that particular process or those processes should depend on the rate of formation of the excited state. Now, excited state molecules may be formed by absorbing photons. Okay, absorbing photon means, as I told you, that it is basically when this matches with, this absorption matches, absorption frequency matches with the frequency of the radiation, then and only then there is excitation. Okay, the excited species may be depleted through a number of different processes, as I mentioned, like fluorescence, phosphorescence. These two are radiative processes, internal conversion and intersystem process. These are purely photophysical processes. Okay. The probability of an excited state species to undergo a chemical reaction depends on how quickly it gets deactivated. Okay. So, probability depends on means if it is quickly deactivated, then maybe it may not get sufficient time to undergo further reaction or to undergo further interaction with other molecules, or maybe if it is not there for longer time, then it may not get time to rearrange itself. So, therefore, the lifetime of that particular species is very important. I mean if it is slowly deactivated, or maybe it stays in the form of the excited species, or if it remains in the form of the excited species, then it can, there is more possibility that it can get sufficient time to undergo other reactions. But at the same time you must keep it in mind that if the excited species remains for a longer time, then there is also a possibility of collisional deactivation. Okay, if its lifetime, if it stays for longer time, maybe say for microsecond or maybe millisecond, then collision with other molecules, maybe with solvent molecules, or maybe some other quencher. Quencher means those molecules which will tend to deactivate. Okay, that is, it is quenching the excited state. So, what is happening, that longer lifetime or longer staying time in the excited state means there is possibility of other deactivation channels to be active. Okay, so since the excited species is there, it is a metastable one. So, it is a less stable one. So, we can apply steady state approximation, especially to the singlet states. Right now, concentrate on to singlet excitation. Okay, singlet to singlet excitation. Okay, so this is S0, this is S1. Okay, so singlet to singlet excitation. Okay, so if we apply, since it is a metastable state, so this S1, concentration of S1, okay, S1 means it is basically M star, maybe M star, this is M, this is M star. So, concentration of M star. We can apply steady state approximation to this, and therefore, we can write d S1 dt to be equal to 0, which is equal to Ka into S naught. S naught means it is the concentration of this is the concentration of S0, then Kf means it is a deactivation channel. So, that means Ka, or in some cases it is written as only Ia. So, anyway, Ka into S naught minus Kf, that is rate of fluorescence deactivation, that is the radiative deexcitation to S0, Okay, this is another, therefore it is in minus sign, then minus K internal conversion S1, then minus K singlet ISC S1. Okay. So, if the radiative lifetime, so if it is fluorescence, okay, from this we can get relation between Kf and other factors, okay, or maybe we can find out the S1 concentration, from which we should be able to find out this concentration of the excited species after applying the steady state approximation, that is putting it to 0. So fluorescence lifetime, from this we can say that if the fluorescence lifetime is tau f, that is your 1 by tau f, we can write it is your we can write the combined thing, that is Kf plus K nr. Okay, nr means is basically Kf plus Kic plus Ksisc. Okay. Or in other case we can write the relation that after putting in this expression we can write that Ka S0 is equal to S1 by tau f. We can write this expression. Okay, so this is your again we come back to this Jablonski diagram, that this is S0, S1, this is absorption Ia, this is fluorescence Kf, this is internal conversion, so Ic, this is intersystem crossing Kisc, this is another intersystem crossing Kisc, and this is phosphorescence. Of course, this is basically your radiative process. Okay. So basically what do we get from this description? From this description, what do we get? That most importantly, that when there is any process that is happening, I mean any process means whether this is a photochemical process or it is a photophysical process, whatever you think about. Basically, when a molecule is excited, what happens to that it gets excited, and this excited molecule undergoes several parallel processes. One is what is called your radiative process, another is called your non-radiative process. Okay. So, radiative process is of immense importance to us. Why it is immense importance to us? Because when a molecule, say if you put a fluorescent molecule or maybe molecule which gives rise to say emission. If you put a molecule and suppose if the environment is such that these channels, say these channels are enhanced, I mean this non-radiative channels are enhanced, then what do you expect? The expectation is that if this is more, then these channels will be weaker and weaker. That means you expect to have less fluorescence. Okay, you expect to have less fluorescence means, so this particularly, I mean this fluorescence quantum yield, or maybe fluorescence intensity. Okay, this fluorescence intensity is a very important thing. Intensity is a very important parameter which depends on how your system, your molecule is interacting with the environment. Okay, if the interaction is such that it promotes this non-radiative channels, then you do not expect to have good fluorescence. In some cases, what is happening, that fluorescence is, or the emission is completely stopped, okay, as a result of interaction with the environment. Okay. In certain cases, maybe it is partially stopped. Okay. So that means something is happening, one of which is basically this non-radiative channels are enhanced. These non-radiative channels are enhanced means you don't expect to have more fluorescence. At the same time, suppose you somehow populate your triplet, this triplet state. Okay, somehow you populate your triplet state by increasing the intersystem crossing rate. So you may ask one thing, that if non-radiative channels are enhanced, then there is a possibility of enhancement of this intersystem crossing also. Of course, there is a possibility, but there are several other, there are other factors which determine whether intersystem crossing will be more or less. Okay, so if it is enhanced, then you expect to have more population in the triplet, but more population in the triplet does not necessarily mean that you will have more phosphorescence, because the thing is that since this T1 to S0, this process, this radiative process is a spin forbidden process. Okay, a spin forbidden process means the system will tend to stay in that particular state for a longer period of time. That means its lifetime is expected to be more. Lifetime is expected to be more means it will have more time to interact with the solvent molecule or maybe some other molecule. Okay, maybe some other molecule means, say we have got another molecule with spin multiplicity, ground state spin multiplicity, triplet. So what will happen? Triplet to triplet collision, and thereby triplet to triplet energy exchange is possible. So that means this triplet will be annihilated, triplet will be lost. So triplet will be lost means your phosphorescence intensity will be still or further lowered. Your phosphorescence intensity will be further lowered means you don't expect, basically, maybe phosphorescence is completely lost. What happens that if you increase the temperature, in a real case, if you increase the temperature, then what happens that at high temperature or some high temperature, since the mean random translation kinetic energy or the thermal motion of the solvent molecules are more, so there is more possibility of triplet being depopulated by collisional mechanism. Therefore phosphorescence will be less. So basically these are very important parameters that we should look into. Another thing, that as I told you, that whenever you change the environment, then there is possibility of various things, like diminution of the fluorescence intensity or maybe phosphorescence intensity, or maybe suppose we have a molecule which generally fluoresces. Okay. Now the thing is that suppose if you add something from outside which makes a complex with the molecule, okay, and maybe it is an excited state complex, then what will happen that, and suppose if that complex is say dark means if that complex does not fluoresce, or maybe suppose there is a ground state complexation before excitation. If there is a ground state complexation, then and only then also you expect to have less molecules to be promoted to the excited state, or maybe less free molecule, that is less free M star molecule M star in the excited state. That means a portion of M star is depleted. Therefore normal fluorescence of this M star will be less. So fluorescence will be reduced. So these are very important thing that we should look into. Okay, and another thing is, as I told you, that there is one important point, that here this photobiology. Okay, so in photobiological cases, like it relates to the light induced biological phenomena. Okay. And this light induced biological phenomena, what is happening, that maybe the molecule, suppose you have got some molecule which does not react under ground state condition, but suppose if you excite it, then certain chemical changes, chemical transformations are there, so that it becomes in the excited state, suppose I mean, of course, in the excited state, the molecule has got different characteristics. So, what will happen that you expect to have different phenomena, and that in the biological field you may expect to have interesting things, although that is under photochemical reaction. Okay. So, in summary, what we have learned from this. So, we have learned about this fate of the excited state species. Okay. So, excited state species means, suppose we have got a pyrene molecule, you excite, it goes to the excited state, singlet excited state, then it may undergo several processes. One may be, say, dimer formation, maybe in the excited state, maybe in the say heterodimer formation, or maybe it can undergo, depending on the situation, it may not be pyrene, maybe some other molecule, it may undergo chemical reaction, and chemical reaction means new chemical species may be formed. And under photophysics you can expect many things means like fluorescence, phosphorescence, then internal conversion, then intersystem crossing, and related phenomena like you can modulate the excited state species concentration. Modulation means, if you say include this excited species maybe in some environment, say in some cavity, in some chemical cavity, so that its this vibrational motions are restricted, or maybe suppose you freeze the system to a very low temperature, maybe say liquid nitrogen temperature. Okay. So, at this very low temperature, those small vibrations are less, and what you expect that if you look into the spectra of these species at low temperature, you can see that ordinarily when you see a broad spectra like general fluorescence spectra, this is your wavelength and this is your intensity, the spectra is basically broad, okay, like something say like this, because of the fact that you have got this vibrationally excited states. When you excite, you may excite maybe to the vibrational excited state, and this is your ground state vibrational levels. So, what happens that emission may be originating from here to here, maybe here to here, something like that. So, you expect a bunch of frequencies, okay, you expect a bunch of frequencies, or maybe emission can originate from here also, here to say here, or maybe here to here. So, this basically broadens your spectra. Okay. Now, when you cool the system down to some lower temperature, then all these local motions, I mean local motions mean this vibrational motions, these are all frozen. So, therefore, what happens is that maybe these small motions are frozen, means they become, these excited species become vibrationally de-excited, and maybe emission is originating from here only. Therefore, this broadening possibility out of this situation is diminished, and therefore, you may expect maybe some sharper spectra. Okay. So, these are the intricate things that we will encounter in as we move on towards the later part of the series of lectures. So, this is a very important point that one should be looking into. Another point is this photo-induced electron transfer that we already have discussed. So, under this photo-induced electron transfer, like pyrene DMA case, pyrene star plus DMA giving rise to pyrene DMA, this is called your exciplex, or maybe pyrene star with another pyrene giving rise to pyrene Excimer. So, this excimer or is this exciplex, you know, these are basically, you know, in a chemically different environment. This is also, this pyrene is also in a chemically different environment. So, exploiting this excimer, okay, exploiting this excimer, we can have, you know, excimer laser also. Like exciplex is excimer is basically ground state, you know, it has, if you look into the potential energy surface, then you know there is no interaction in the ground state, okay, interaction in the ground state, but in the excited state there is interaction. So, excited state maybe has got some definite minima, but ground state there is no interaction, okay. So, maybe you can expect difference in you know emission behavior, something like that. So, this is your energy and this is your you know distance. So, in ground state there is no interaction, but in the excited state there is interaction. So, that means, so and of course, since there is a definitive state, so and the important point is that the moment it goes to the ground state, if it fluoresces, then after fluorescence is done, then you get back the original pyrene and two pyrene molecules. In the same way, if you can generate, I mean if you can have similar excimer system, that can be exploited to you know have excimer based laser. So, that we will discuss maybe in some part of our discussion. And another important point, although that I will take up you know in the later part of our discussion, that this you know this fluorescence, whatever I told, I mean up to today's lecture I talked about this spontaneous emission. Spontaneous emission. Spontaneous emission means the moment you generate the excited state, so that is M star, it has got the probability to undergo de-excitation spontaneously, okay. But suppose if it so happens that probability of spontaneous de-excitation to ground state is less, then it may so happen that you can bring in another frequency into it, so that this that will stimulate this M star to undergo de-excitation, okay, to undergo de-excitation, giving rise to photons, and that is called your stimulated emission. Stimulated emission. And this stimulated emission is the basis of laser, which what I will take up maybe in some later part. So, so the point is, so this will be taken up, but up to this, up to whatever I told is basically all is based on spontaneous emission. And these processes, I mean fate of the excited state, as I told you, that fate of the excited state, I mean your photophysics, photochemistry, photoinduced electron transfer, maybe rearrangement, maybe photochemical, other reactions, everything, in summary I can tell that everything should depend on the lifetime of the excited state. Lifetime of the excited state means lifetime, I mean time for which it stays in the excited state. And how to, I mean if you somehow can increase or increase the lifetime of the excited state, then you can expect complication, or maybe in some cases maybe some complications can be tuned in a different fashion. So lifetime is a very important parameter that one should look into while discussing photophysics or photochemistry or photo-induced electron transfer. Okay, so and this lifetime means it is basically when a molecule is fluorescing, suppose it gets excitation, and then after excitation it gets de-excited. So de-excited means if it is a radiative de-excitation, then you expect to have photons. but the point is it is very difficult to measure using a apparatus which is generally fluorimeter is a steady state apparatus. What it does is, I mean, fluorimeter, what I discussed in our last lecture, is a steady state apparatus. Steady state apparatus means you shine with your radiation, then emission is collected. So, basically emission is collected for some time, okay, for some time, and say for 1 second. Okay. So, emission means for 1 second this much of photons are collected, then corresponding signal is converted and given to the computer for plotting your spectra. Okay. So, it does not give you any details about the the time evolution of the process. Okay. So, for measuring the time evolution of the process, you need to have an apparatus which is called a time resolved fluorimeter. So, while connecting the importance of lifetime of the excited state with photophysics, photochemistry, photoinduced electron transfer, it is also necessary to know how this particular parameter can be, I mean, this particular number, maybe say it is a 1 nanosecond, say lifetime is 1 nanosecond, what does it mean? So, how this important parameter can be, that we should also learn, maybe in some forthcoming lecture we will discuss on that. So this completes fate of the excited species, and in the next lecture we will still continue with this discussion. Some other detailing are required, so that I will take up in the next lecture. So till then, thank you.